So it's my great pleasure to be able to introduce Shan Lu. Shan is a full professor at the University of Chicago. So first of all, thanks for agreeing to give this keynote, Shan. And Shan has been doing a lot of amazing work at the intersection of multiple communities. I guess one is the software reliability or software engineering community, where she has been presenting her work at venues such as ICSI or SFSE, and also the systems community, where she has been presenting, for example, at venues such as SOSB, OSDI, perhaps also S+, and so on. And I think today in this talk, she is going to tell us a bit about the recent Hyperloop project, which aims at detecting and solving performance problems for web applications. And like many of her works and projects, it has had significant impact in practice. So for example, it allowed them to report countless bug reports. It also received a lot of attention in media, for example, on the morning paper in Hacker News and so on. And it also won a distinguished paper award at ICSI 2019. So with that, very much looking forward to the talk, Shan, and the stage is yours.
Okay, thank you, Manu, for the introduction. Let me share my screen. Can you see my slides? Okay, yeah, great. Yeah, I'm very happy to get this chance, to talk with you about some of the things that we have been doing in the last few years about tackling performance and correctness problems for web applications that have a database backend. And before I start, I have to say, a lot of this work is done by my former student, Junwen, and my collaborator, Alvin, and his former student, Tong. Okay, so I will start with web application, right? So web applications are everywhere. They're doing collaboration, shopping, social network. We all use tons of web application. And performance for these web applications is extremely important. So there have been a lot of study about how any extra 1 second of delay could potentially hurt the business a lot. And there's also typically a consensus that the limit, right, for a good web application's latency should be about 2 seconds. Otherwise, some users will feel impatient. But having said that, although this is everybody know, still there are a lot of performance problems for web applications. And you can easily find a lot of these examples. Like a few years ago, there was an embarrassing report about that only 6 people went through the healthcare.gov on the first day, just simply because the web application is so slow. And more recently, there was also study that there's a huge amount of money that is invested in putting up this vaccine registration appointment website, and the performance is extremely poor. And when we started, so we take some popular open source web application like GitLab Spree, which is a shopping platform that is widely used, and we synthesized some data just based on some statistics that were collected from real world these web application. And we synthesized the database size that is, we would see pretty medium, like 20 gigabyte for the main table. And we draw the page loading time across all the pages of these applications. And the kind of concerning thing is that even with a very, I would say, medium-sized database, we see that 20% of the pages take more than 2 seconds to load. So that's kind of our motivation, right, behind try to understand what is the performance problem, how to solve them. And before I tell you, right, what exactly is a problem, what's our solution, I want just to spend a bit of time just to tell you a little history of web page. How can, why did we come to the current state? So in the old days, web pages are very simple, right? It's static. So if I want to build a web page that show a list of titles of all the blogs, for example, it's very simple. You just write HTML, and the page loading time is only determined by your network bandwidth. That's it. But then, actually a while ago, right? Now dynamic content become very important. And because of that, you do not want to just have a static HTML file. So instead, now there's an application server that will particularly generate some dynamic content. And the content that can potentially be dynamically changed, and it is in a very commonly in a JSON file. And the application server, right? It will read the file and potentially operate on on some variables. And now the HTML file is not static anymore. In the HTML file, it will actually it will use the variables that is dynamically generated by the web application. So in this case, these blogs. So that's where we started getting, if you want to, if a page loads slow, it may be a networking problem, or maybe there's something wrong on the application server. Maybe the web application is written in an inefficient way. And then things get more complicated, right? So now we have more and more data. People realize, hey, just using a JSON file to hold all your blogs, this doesn't seem to be scalable. So now we start to have database engine as the third layer for most web application. So now instead of having a JSON file, it now become a table, right, in your database. Title, content, ID, everything is part of the table. And if I want to, right, fetch this table, now I have to use, it's no longer just a file read, right? I have to use SQL query. I have to do a select. And now because of these, right, how can web application developers, right, to access this database? We do not, right, want web application developers to all learn SQL. So because of that, then there is a framework called Object Relational Mapping. It's a very popular framework. There are many instances of it for Ruby on Rails, for Ruby, for Python, in Java. And now with this, every table corresponds to a special type of class in the web application. So developer does not need to learn SQL at all. They don't even need to be aware that there's a database engine. They just need to declare a class of a particular supertype, and then that class will be automatically translated into a database table. And then they also don't need to learn about SQL query. They just need to write things such as, like, say, blog.all, and this, which almost looks like a heap access, right? That accesses all field of object blog. This will be automatically translated into the select query. So that is what most today's web applications are organized. It looks great. It looks like you don't need to learn anything about database, and you can write a pretty large scale web application. Now, the problem is there are a lot of particularly performance problems. And there are also correctness problems, which I will talk about later. And if you think about it, it's actually pretty natural that there will be performance problems. The reason is, as I mentioned, now the web developer, they actually have no idea. Many of them, right? They often have no idea what queries are actually issued at runtime. They may just simply because they treat these like ORM APIs such as .all, right? They treat this as black box. So they may write code that they think I'm just doing heap access, right? And it turns out these are doing very inefficient database query, which is very expensive. And from database perspective, right, there are already a lot of database, engine query optimization there, but because database engine does not know the semantics of application. So as a result, you get to see many very inefficient database design. And you easily get 10 times, 100 times of slowdown just because of this gap between the application layer and the database layer. So that's one of the themes that we want to tackle in our research, to bridge these two layers and to enable application and database cross-stack optimization. So that's one theme that you will see that I talk about in my talk. The second thing we realized is that there's also a big gap now between the web interface design and the underlying application server and database server. So a very simple example. So, and this is a real example. There was a web page and people say, hey, why is this so slow? And then they did a lot of debugging. And then they find out that they have a very tiny entry somewhere indicating, showing, for example, say how many comments are there. And it turns out this very tiny piece that many users didn't even notice, that is the most complicated part because it requires a join query to generate. So the takeaway from this very simple example is that when people design a web page, right, they can no longer easily know what's the cost behind every HTML content. So this is a challenge. And just to go and give you a little bit more detail, right? Like the exact, for this toy example, if you look at the HTML file, you just see that, oh, here, I have this P /P indicating HTML element, and I'm just showing comments. And how do I get the number? Oh, it's from a variable count, right? You look at this file, you have no idea what's the cost to generate this variable count. And if you're able to track it back to the application, you will see that, oh, there's a comment.join.where. Okay, now this .join.where is an ORM API, right? For people who are familiar with SQL, you will immediately realize, probably, right? And indeed, this will then later on be translated into a SQL query. There's a select count, join, and all these, right? So this is just too much information for a web page, an interface designer to know. So just this very simple, this comments thing. And in our experiment, just a 20K record database, it takes more than 1 second to generate. So in the original example, at the end, the developer just decide, okay, we really don't need this element. I'd rather that my page can load much faster. So here it indicates that there is a lack of database-aware interface design tool. Okay, so that's kind of the overview, and that is exactly what we have been looking at. So back in 2018, so we did a study about the performance problem for modern web application and create some kind of taxonomy about performance problems. And then we tackle these problems one by one. I will spend a lot of the majority of my talk today just talking about this user interface. How can we do database aware interface design? And I also talk a little bit about how we extend traditional compiler optimization to understand database SQL complexity so that we can detect some inefficient ORM API usage. We also had some work in the past about how to change the database design given application semantics, which I won't have time to talk about today. And these are just performance. So we also have work try to basically just synthesize everything from scratch. And that's kind of like a vision thing. And these are just a performance thing. And hopefully if I have time at the end, I will also tell you this kind of gap, right, between the interface design application and the database. It also leads to all kinds of correctness problems. So one type of correctness problem we found is that there's something we refer to as data constraint, such as what should be the maximum length of your password or username. And these are often specified separately at these 3 different layers. And this leads to a lot of correctness problems. And we also found that sometimes people make database schema change, but they do not make change accordingly at your HTML and application layer. And this also leads to problems. Okay, so that's kind of the roadmap. So I will just skip this. As many mentioned, I mean, this sequence of work, it has led to a lot of awareness in the industry, in morning paper, and we found thousands of bugs. Okay, so start with a kind of understanding the problem, right? So how did we start it? So we kind of started informally. We had a chat. I had a chat with my collaborator, and he said, hey, I think there are a lot of problems like this. And if you search, there are a lot of blogs talking about this, but there's no comprehensive study. So what we did is we picked some application, represented open source application, and we mainly want to understand three things. We want to know what are the common main types of problems, how severe are they, right, and how complicated is the fix. So if they are severe and if they also have relatively simple fix, right, that would be great, right? That means a lot of automation potentially we can do. So we went to GitHub, and at that time, Ruby was the most popular web application developing language. And these are we found that every application has a label indicating what's a category of application. And these 6 are the most popular 6 categories. They cover like 99% of all the web applications written in Ruby. And so for each category, we take the 2 most popular Ruby application on GitHub. And this popularity is measured by the number of stars. So we take this 12 application, and we did 2 things to collect performance problem. One is we check their bug database, and from there we collected 140 performance problems that were complained by end users and were fixed. And we also synthesized database for each of these applications. It took a lot of effort. We synthesized using some statistics that we collected from the real deployment of this application. And then we do profiling. And then by doing profiling, we identified 64 problems in the latest version of this application that led to more than 2 seconds of page loading time. And we find out that for each of these cases, there are inefficiencies. So we studied these altogether, we studied 200, and we find that there are problems across the layer of interface, application, and database. And we have very detailed taxonomy identifying, I think in total 9 anti-patterns. I will skip them because you will see examples of many of these later. But at a high level, we see that actually among these 200 we have seen, the most common ones are inefficient use of ORM API from application layer. But there are also a significant amount in the interface design problem and in database design. We also look at how severe are these problems. So what did we do is we look at those 64 cases, right? Those 64 slow pages in the latest version of this application, and we manually fix them. And after we manually fix them, make them more efficient, we measure the slowdown that were caused by the original inefficiency. And then we count for how many of them can cause, say, more than 5 times of slowdown, how many of them can cause 4x to 5x slowdown. So the takeaway is that you can see these inefficiencies, they matters a lot. So the slowdown here is not just about, one query, I did a optimization. No, this is an end-to-end page loading time. It includes networking time, including, the web browser, the client side rendering time, everything included. So we can see that more than 60% of the cases, they leads to more than two times slowdown for this end-to-end page loading time. So it's very severe. And particularly, I want to highlight there are like 17 cases, they lead to more than 5 times the slowdown. And the majority of them is because of interface design. So because of this, how to do better interface design is something that we'll talk about first, immediately next. Okay, so we also checked how many lines of code are needed to fix this problem. It turns out for the majority of cases, we need less than 5 lines of code. Right, so that really seems like, there should be something, right, we can do automatically. So that was our, for more detailed study result, you can refer to our paper. This was the first comprehensive study of real-world web applications performance problem. So because of that, it was very well received. This was what was, people's feedback from on the Hacker News morning paper and so on. Okay, so now let's see, right? I have already hopefully motivated you well enough. Let's see what exactly is this user interface design thing. Why did we look at it? There were a lot of complaints, and to be honest, this motivation directly came from this profiling, this study that we did. And so just to give an example, right, what exact type of this inefficient user interface, web interface design we're talking about? So we will show you, I will show you a very short video clip. So basically on the left-hand side is one web page, right-hand side is another web page. And in the video, we will click and load them at the same time, immediately the same networking environment, and just see how these two pages get loaded and rendered. Okay, right. So we actually highlighted. You can see on the right hand side, page 2. There's a cycle. So actually we added that in the video just to help you understand what's the difference. So you can see that the only difference between these two is that there's one small segment of this web page is asynchronously loaded on the page 2, on the version 2, right? But it's not, it's synchronously loaded on version 1. And I don't have time to do a polling, but we did use a study, and as you can imagine, the majority of users, they prefer page 2 much more than page 1, right? It's a very simple design change. And you can imagine why this particular segment takes so long to load, because there's a very complicated database query behind it. Okay, so that's the type of interface, database aware interface optimizations that I was referring to. It's actually it's completely out of scope of traditional code optimization, because traditionally for compiler, right, when you do optimization, you want to make sure the output, the behavior of software does not change. But that's exactly right opposite from what we want to do here. And we need to be careful, right? Because if you only want to improve performance, I could just say, hey, let's just remove all the content from web page, right? That's not the type of optimization you want to do. And that's the first challenge, right? This is different from traditional. You cannot just automatically, right, decide that, oh, I want to improve performance, let me delete things. Secondly, as you can see, right, in order to do this code transformation, the potential analysis has to be able to go through all these layers. You have to understand HTML code, Ruby code, C code. So there's quite a complexity there. Okay, so what we end up doing is, because we know we cannot do this completely automatically, because we want to get, right, developers' human opinion, right, about, do you like this trade-off, right, between interface change and performance improvement? So instead, the first component of this tool, which we call the panorama, the first component of panorama is a database-aware cost estimation and visualization. So for a web page, right, I will tell you, you can see how we do this soon later. But basically, given a web page, if you use our tool, we will show you a heat map that kind of tell you how much database cost is behind generating each HTML content. And then starting from here, and then we also tell you there are different alternative design potential you can do. So for example, if you hover here, and then we will tell you potentially you could remove it, you could do approximation, you could do asynchronous loading. And in our interface, the user can try it, and then they will see, right? For example, when they try approximate, right? They will say, oh, actually, I can just show that the comment is more than, say, in this case, 20 plus. And then they will see the heat map will change, right? They will see that, oh, this simple interface change actually will drop the database processing time by a lot. And similarly, for example, if you click this, and we'll tell you there's a type of change called pagination you can do. And if you do this, it's a very typical web design trick where you just paginate. And you can also very intuitively see that the cost will drop a lot. This is a database cost drop. Okay, so so in the next, like say 10 minutes, I hope to tell you that, how exactly we can do this refactoring. I won't have time to talk about this cost estimation, but it's kind of embedded. The technique, it's actually kind of, you can tell the technique just based on how we do the refactoring. And particularly, I will tell you what kind of, how do we decide, right? What type of refactoring are the candidates, when it will be suitable to do, and how exactly to do it. So what type of, right, design change, right? As we said, not all design changes are meaningful, right? So we kind of looked at a lot of real world web application, and we kind of create a taxonomy that we think there are mainly two types of design, of alternative design. One is that we display the same content, but in different format. So one type is this asynchronous loading, right? I load something asynchronously. It's the same content. The second, like the pagination, right? That's also an example that you ultimately get the same content, but it's displayed in a different way. The second major type of alternative design is the content itself gets simplified. Of course, in this case, potentially, you may or may not want to do it, right? Depending on, there probably need to be a bigger performance incentive for you to do it. One is we just remove, okay? But of course, not remove all the content. Potentially just remove, say, the most expensive tag. The second type is approximation, right? As I showed you. So these are the four types that we target, and we believe that potentially, right, people can also extend our framework to incorporate other types of alternative design. So now the next question is, when do we do the refactoring, right? So if you're familiar with compiler optimization, right, so you probably know, right, there are data flow analysis you can do, and then there are certain conditions that will determine whether optimization makes sense or not. Now, for our interface refactoring, this is very different. Because most developer, right, if you think about it, can I do pagination? Well, the decision process is typically very subjective. Typically, you probably would think, well, if it's a long enough a list, then potentially I can do pagination. So the challenge here is we have to turn this very subjective, informal, right, reasoning into a very formal, right, code analysis, data dependency, right, that kind of formula, right, very formal condition that our automated code analysis, right, can automate. So, so let's first manually go through this process, and then it will be clear what should be the condition. So for this piece of code, right, if you look at the web page, you will see that this basically is displayed in the way that you have this span. So this HTML tag basically just tell you, oh, this will be an entry on the web page. And what I highlighted here, this percentage sign, this actually means anything enclosed by this is a Ruby code. And so here inside, this is not HTML syntax. So this is just Ruby. And you can see that basically what they do here is a for loop. They go through each blog, they will show the title and the end of the loop. Okay, so then where does this blog variable comes from? So if you look at the code, if you know Ruby well, eventually you'll find out that, oh, here I have an index function, and then this blog is generated by this blog.where. Okay, now given this example, right, how do we formalize this human concept of a long list of items on web page that potentially I want to paginate? So probably you can see, right, a list of items on web page that seems to correspond to, right, this code structure here that I have a for loop, and in every iteration of this for loop, something get displayed. And what does it mean, right? How can we tell compiler to check whether something is a long list or is a short list? So potentially, right, we can let compiler to analyze a loop bound, right? How many iterations this loop will take. And in this particular case, the number of iteration is the size, is a scale of the results returned by this blog.where, which is a select query. Okay, so now you can see, so this basically comes down to two questions, right? If our compiler analysis can see what code application, right, is used to generate what HTML tag, right, and to analyze this HTML tag to see whether it's inside the loop. And then secondly, right, if we can automatically judge, right, whether the code, right, could return something that that potentially can scale with the input size, right? These, if we put together in a nice way, then potentially we can automatically decide, right? Here I have a long list of things and I want to paginate. Okay, so and an opposite example, right, would like here we will see, oh, here you have HTML tag is not in a loop, and it just basically just you just display a scalar value. So this is definitely not a candidate for paginate. And basically that's why, like, eventually, right, we do all this analysis, and then in the interface you will see that pagination is suggested, right, for this blog title list, but it's not suggested for the comment. And then just to give you one more example, like for asynchronous load, right? As I showed you that example, right? We automatically decide, oh, maybe you want to asynchronously load a particular part of the code of your HTML. Why? So which HTML tag, right, is a good candidate for asynchronous load? If you think about it, it depends on the cost, right? So you probably do not want to asynchronously load the element that takes, like, for example, in this case, the comment, right, it takes longer time to generate for database to process than this blog list. So if that's the case, you should asynchronously load the element that takes the longest time, right? Because otherwise, if you just asynchronously load the blog title, it doesn't help, right? Because the page will still take really long time to load. And so this event essentially comes down, right, to still, first of all, I have to know for every HTML element what code is used to process data and generate it. And secondly, I need to do some kind of complexity analysis, right, so that I know which tag is the most complicated one, so that I want to asynchronously load it. Okay, so the first question is the same, right? And then here we have an extra challenge to do the complexity analysis. Okay, so now that I have kind of decomposed this problem, and you probably have a sense about what we will do. But just before so it's actually more complicated than this. Like for example, for asynchronous loading, we also need to check whether the tag, the computation used to generate this tag, whether it's also needed by some other tag. Right? If it turns out also needed by another tag, then it does not make sense to asynchronously load just one of them. So I will skip all those detailed analysis and just to look at this most basic three questions that I talk about. First of all, how do we know which application code, right, to use to generate which HTML tag? So this one actually turns out a very relatively easy extension for the Ruby compiler will be able to do this. So to know, right, what code is used to generate what data. If this was just within, say, Ruby, this already can be easily done, right? Because we can just use a program dependency graph. Like in this example, if I want to know how count is generated, I just need to look at the program dependency graph, and I know that, oh, it's generated by join. Now, what traditional compiler cannot do, right, is that it did not know that this count variable is the count variable used in this HTML file, because the compiler for the HTML and the compiler for the Ruby file, traditionally, they don't talk with each other. So now why, right, these two match with each other? It's actually because there is in Ruby, there's this convention that at the end, they will say render, and then they will put the HTML file there. So basically, they will do this HTML file name, they will do a matching, and if they match, then we know that, oh, the variable that's referred to by this HTML, they are generated by the corresponding function, right, that put the render at the end. So we just extended Ruby compiler, right? We just need to understand, be able to pass, right, this render statement. And then what we do is, once we pass this render statement, we go to HTML, and in the HTML file, right, we search for that % sign and extract all the Ruby code out. And in addition to that, we also need to understand a little bit of HTML so that I will know that, oh, this Ruby variable is used in which tag. And we will remember this information because this will help us eventually to generate that heat map, right? I will know that, right? This count, its cost is related to that particular HTML. Okay, so we extract this information and we essentially just embed them into the original function, right? It's kind of like we replace the render, right, with a list of HTML tag information and variable information that is used in the HTML that is going to be rendered. So essentially, we just extend the original program dependency graph with those extra variables, right, that are in the rendered HTML file and with the HTML tag information. So basically now, right, with this extended program dependency graph, right, you can see we can easily, you ask me which, hey, this, you give me an HTML tag, right? I can map that to a variable in this extended dependency graph, and I can just easily, right, do dependency checking and identify all the program statements that is used to generate this tag. So now the next question is, right, I need to understand, I need to, potentially with that, right, I can know the computation cost in the application side for each HTML, but I still don't know the database cost. So now this requires some kind of extension of Ruby compiler to understand SQL information. So we did that extension so that, for example, for certain ORM API, we extend the Ruby compiler so that it knows, understand a little bit of semantics, right? So that it knows that, hey, this dot join, right? This is a join query. That dot where, that is a select query. So we give this information, and we also have do a little bit of kind of like scale analysis. So we know, we basically just say, hey, if there's no limit something, right? And if it's not an aggregation query, then we just think the returned result has a finite size. Otherwise, this is something we call a scaling query, which would, if it map to a web elements, right? And then you know that it's a candidate for pagination. And then for cost, for query cost, right? Similarly, like as long as we know that, oh, this is join queries, as a select query, then we can associate complexity with it. And we'll also, a little bit of complexity that I skip here is that we'll also combine this with application complexity, right? For example, if the join query is embedded in a for loop, then potentially it will be a n cube instead of n squared. So we'll do all these analysis. With all these, right? So with all this information embedded, right? If you think about, oh, actually, then we can answer the question about when you could do pagination, when you could do approximation, and so on. So with that, and of course, then we can not only identify the problem, right, but we can also naturally just do some code changes. And because our compiler analysis now also get extended to HTML, so we can do changes. We can help you change not just your Ruby code, but also HTML code. So I'll skip all these details here. So we did just very quickly our evaluation. We found that there are a lot of optimization, kind of user interface optimization opportunity across those 12 most popular Ruby applications. And for these, right, because we changed the interface, so we did a user study. So we tried like 15 cases across 4 different types of interface design, and we get 100 participants. And we show them 8 groups of pages, right? Every group contains multiple alternative design. And we ask them 3 questions. First of all, we ask them, hey, what kind of page loading time do you like? In this case, it's not, we do not show them side-by-side video, okay? We ask them to click the page themselves, right? And sometimes, and the order of their clicking of the link is random, so they couldn't tell, right? What is original, what is optimized by us. So we just ask them, how do you feel about page loading time? So actually, I mean, it's not, people's feeling is very different from our computer's measurement, right? In our measurement, we know that the new page we generate always load faster. Human does not necessarily feel that way. But at least, well, in the majority of the time, they do feel like the page that generated by or changed by us load faster. We also ask them, how do you like the content that gets rendered? So that result, as expected, right, is a mix. Interestingly, when we do pagination or when we do approximate, people feel like these more people prefer the original page. In cases like when we do asynchronous loading, and sometimes we just simply remove some content. For some reason, more people actually prefer the new way of content. And we ask them overall, right, what page do you prefer? And in most cases, they prefer, right, considering content and performance, they prefer the page that we have changed much, much more. Okay, so basically that's, that finish, this panorama that does this interface design. Now, let me just very quickly go through several other pieces of work. As I mentioned, among the problems we have seen, about half of them is because the developer are using ORM API in an inefficient way. There are a lot of complaints about it, and I will give you some very quick example. Like I feel like it's a funny example. It's like there was a page that was very slow, and then the solution, when you look at the patch, they just replace something like blog.present to blog.exist. Okay, so what are these two API? Both of them are legitimate ORM API, and they do the same thing. They allow you to check, okay, whether say this blog container or table, right, whether it contains any record or not. Okay, so basically, does it exist? Is there something like that that is present? So semantically, it's actually exactly the same. So why did they make this change? Again, like if you use a very medium-sized table, like 20,000 record, and you will see that there's 1,000 times of performance difference between them. If you use this .exist, it can finish in 1 millisecond. If you do present, it takes more than 2 full seconds to finish. The reason is, it turns out the first is present will be translated to a select star query. The second, and you get all the record, and all the record will be sent to the application server. And the application server then will check whether you have more than one record, and then it will return a Boolean to this if checking. And then this .exist, it will translate it to a limit 1 query. So when it finds the first query, first record that satisfies this condition, it immediately returns. Okay, so you can imagine, right? This is really difficult for web developers. And there are other examples, like for example here. So in this case, they go through every blog entry, and then they check whether the title of the blog is in a block list or not. If it is, it will remove it from the block list. If you just look at this, right? I mean, unless you're an ORM expert, otherwise you look at this, we don't see any inefficiency. Now, turns out this blog list.all, this is not a heap access. This will be translated into a select star query. So what happened is that this select star, right? Every time you return the same thing. And for in this loop, in every iteration of this loop, you are sending the same query again and again. The fix is not hard, right? Essentially, you're just doing you just need to get that blog list.all at the beginning, and then you just use it in every iteration. Then there are other examples, like you just keep reload and you don't use the result. So these are all examples of misuse, right, of ORM API. And they can lead to huge, right, performance difference. So the challenge here, right, is that why this problem exists, right? Is because now the compiler, Ruby compiler, does not understand ORM API. They don't understand SQL, right? These are all treated as black box, so there's no optimization. But even if we extend, right, you can already see, right, we already did this extension. there's still a challenge because there's a huge variety of this kind of inefficiency. And it's kind of boring to build, optimization to one by one. So the solution, right? Solution is, first of all, yes, right? We do need to extend our compiler to understand ORM API. And you already see that we did it. For the second one, it turns out there's an easy solution. All these examples, and including others that I haven't told you, they actually corresponds to very traditional compiler optimization. Like the first one is just a stress reduction. The second one is just a very typical loop invariant motion, right? The third one actually is just dead code elimination. So actually it turns out as long as we extend the traditional API in the right way, and then I just apply the traditional compiler optimization, and all the problem will be solved. So that's exactly what we did. And I would just I don't have time to go through this, but basically the idea is given a program, right? This will be the traditional program dependency graph that will be generated by the Ruby compiler. We will extend it so that we know which node corresponds to a database query, whether it's a read query or write query, and what table and what column each of them depends on. And this, we extend, right, data flow analysis and control flow analysis with this, database table, read and write information. And just with this, we can easily do extended dependency analysis and data flow optimization. Okay, so I'll skip all the details. So with this, we can solve the inefficient problem in a much more comprehensive way, and this allows us to find more than 1,000 problems in these 12 most popular web applications. And for hundreds of them, they are already confirmed and fixed in this application. Okay, so a quick summary of this performance problem. In general, a theme is that because there's a cross stack, right, optimization is missing. So because of that, there's tons of performance problem. And also the user interface optimization is a big challenge in the past because it's not a traditional compiler optimization. Okay, so maybe I will use like 5 more minutes to just quickly tell you, some of the correctness problems. One big type of correctness one we call the data constraint conflict. So just like, because you can imagine, right, because there's a lot of data, right, there are a lot of data in the database. So there need to be constraint associated with almost every piece of data. So for example, say like in this case, right, there is a constraint about what's the maximum length, what's the minimum length, and sometimes you also specify what's a format, what character is allowed, right? These are all called data constraint. So we did a study and we saw that about 77% of fields in these, again, this 12 application, there are some constraint associated with them. So they widely exist. And we also see that these constraints, they are checked across all these 3 different stacks. There are ways to check them in HTML. They're actually built in Ruby function, and similarly for Python and for Java. They're built-in function to do this check before every time that the application save it to the database. And there's also constraint, there's also checking that is done inside database engine. And we also see that there is a frequent update to these constraints. And you can probably tell, right? This means a lot of problem could happen. And indeed, so we did a checking using just using static checker. And we found out that again, in the latest version, right, in this 12 popular application, and we see problems such as the application, right? There are more than 200 fields. The application said it cannot be null, okay? But they're set to be null by default in database. And we see that sometimes the application said the field is required to be unique, but it's not checked in the database. And in all these cases, they can lead to page crash at runtime. And there's also a lot of inconsistency across version. And sometimes you just upgrade your database schema, suddenly application cannot be used. And the last piece we investigated is to see that when database schema is changed, how often you will change the code correspondingly. And I will skip all these. The idea is that there is a So you can see the data schema change in these web applications is not very common, as you can imagine, right? But still, for pretty much every version, you will see a couple of data schema changes. And this include table name change, right? And sometimes more complicated, like affiliation, relationship change. And of course, right, like they all require some corresponding code change. The simplest one, like if I change a table name, right, then then you have to change your, if I change a column name, right, you have to change your application name. So that you will, like for example, if I change from title to header, right, you have to change your code correspondingly. And so basically we did some checking, and again, right, in the latest version, there are still inconsistent changes. Again, right, when you have multiple layers of code, some help is needed. So as a conclusion, right, why were there so many problems, right? And I think just in general, right, there's a huge gap among web users, among developers of web applications and database engine. And with these semantic gaps, and also because of the large scale of this modern system, right, the testing is difficult. And developer cannot know, right? Often can only know the information about one particular layer, not all. So that's why there were so many problems: performance problem, correctness problem. What's the solution, right? We showed you that we did some detection, we have some user interface, we do some automatic refactoring, but we think that potentially, right, in the future, the scale will further grow. Potentially, we may need some synthesis, right, to automatically synthesize, hopefully, the majority of the web application. And there probably will need to be better testing to test not just traditional code, right, not just to test the database itself, but also test and the user interface, right? Test them in a holistic manner. So I will end my talk here, and again, thanks to all to my collaborators, and thank you.
Okay. Thanks a lot for the very interesting keynote, Shan. So are there any questions?
Yes, we have questions here.
Hi, thanks for the excellent talk. I was just wondering, web frameworks are constantly evolving, and, something is very popular at one point in time, and then they sort of change, and they change in a much faster life cycle than traditional software systems. My question was, how do you see some of these approaches evolving as the application logic starts moving closer to the user in the case of these JavaScript libraries, for example? So some of the templating that is typically done using Django or Rails was usually server side, but now people are starting to shift that towards the client side. So how do you see some of these approaches evolving? Does it make things easier? Does it make things harder? Can we still do this cross-platform analysis as we move more of this logic into client-side JavaScript?
Yeah, that's a great question. So let me say a couple of things. Yeah, it's a great question. So first of all, we actually see some of this problem is happened exactly because of very quick evolvement. Like, for example, we see that kind of funny or silly example of present, right, exist. You would wonder, why do you have these two API? And it turns out it's because, one is from some earlier generation ORM and one is from later generation ORM. And then I'll come to this JavaScript thing. That's a great question. So when we did this study, we actually initially, we were not sure how much performance cost is from the server end, how much is on the client end. So I didn't present that number. So roughly about 60% is on the server end, and about 40% on average is on the client end, right? And then when I say on the client end, most of them is in JavaScript. So these really vary across web pages. So for some web pages, most of the cost is on JavaScript. So the other cost does not matter that much. But I would say that still, right, just based on what we have seen, at least a couple of years ago, I think the majority of the cost is still on the server side. One more thing I want to mention is that we have seen that, for example, sometimes a lot of code is in JavaScript. And we have seen, and I will skip the details here, and we have seen that this kind of inefficiency sometimes it's also because the JavaScript, right, is using the data in an inefficient way. And sometimes there are cases that we were thinking, oh, we wish we could also extend our analysis to include JavaScript, right? Then it will be a full-blown optimization. But it turns out to be really challenging, so we didn't do that. So I think it's a very good question. I don't have an answer, and I think yeah, how to do optimization across all these, including JavaScript. I think that would be very interesting.
We have one more question here in the room. Two, actually.
Hi, I'm Stephanie Scherzinger from the University of Passau. Really interesting talk, especially the part about schema evolution and the coupling with the code sparks me. Have you looked at web applications that have a NoSQL backend that's schema flexible, because there you don't have this strong coupling, or rather you can push the schema evolution inside the code with object mappers and such?
Yeah, that's a great question. So, I mean, the short answer is we have not. I mean, it is something that has been in my mind. Like there are a lot of applications that has non-SQL. We have not looked at it. Yes, you're right. I mean, I suspect, like for example, in our case, right, the most complicated schema change or the most error-prone is the association relationship change. Like sometimes between two tables, right, they change from 1 to 1 to 1 to n, and then the resulting change is very complicated. So I think when you look at non-SQL, right, if they don't have this kind of association, remote key, all these things, I think on one hand, you wouldn't see kind of strictly speaking, right, inconsistency between schema and the code, because now the schema become much simpler. But I suspect in that case, you probably will see more semantic errors, right? When the code evolve, it's like you no longer have this very uniform, right, template of schema, but your schema actually now becomes part of just the code semantics. So that's what I suspect. But it's a great question, and I think it'll be interesting to look at that.
Really great talk, really interesting work. So thanks for that. I was just wondering if you looked at all at kind of more tightly integrating with the database. So, oftentimes the query optimizer will have some estimate of the cost of a query that might be more easily accessible than the estimation that you're trying to program analysis. Have you looked at all at trying to leverage the database for that?
Yeah, so again, that's another great question. Yeah, so in the panorama work, we did not, because at that time we feel like, looking into the query optimizer and get the estimation there seems a bit overkill, because it turns out for these applications we looked at, it turns out that it's like, for example, whether the complexity is n raised to 3 or n raised to 4, or what's the coefficient, that it doesn't matter that much. And because ultimately we will let the user to make the final decision. So that's why we did not look at it. So we had some follow-up work, which we are still working on. There, actually, we are trying to do some more, optimization. I would say more sophisticated, not just like, oh, you use API wrong. And when we are doing that optimization, we realize sometimes, like, so potentially I want to replace one query, right, to another query, or chain some query together. And we do realize, right, sometimes we using, database query optimizer, using that, a complexity estimator, it will save us, right, it will help us to make a decision about whether, whether one version is likely to get a performance improvement than the other version. Yeah, so I guess the answer is yes. I think the leveraging, right, existing database engines, those information is definitely helpful in some cases. In some other cases, it's kind of like what we're looking at essentially is a low-hanging fruit, right? It's kind of like, so you don't even need a very accurate performance estimation to be able to help developer. Yeah, so in that cases, we did not use. Yeah, but it's a great point.
Okay, so no further questions here. Do we have questions online?
No, also not at the moment. But I have a question that I was curious to ask. So perhaps it's a more philosophical question, but if we could redesign how database-backed web applications are built, like the kind of abstractions also, do you think that like it would make sense to see this as a kind of language design problem and implement new kind of languages in how we describe them? Or not sure if you have thought about this.
Oh, so you're saying if we redesign everything?
Right, right.
Yeah, so as we said, so we have a CIDA paper, which is kind of like thinking about, hey, if we redo everything, what would happen? And at that time, it's kind of like we have this hope or dream, right? That hopefully the user only need to specify, what kind of data they want to eventually see. And then maybe we can synthesize everything. We can synthesize, because this is the data you want to see, then this is a query that will be needed. This is an application code that will be needed to do post-processing. And then we can automatically do all the optimization for you. And then maybe there will need to be some domain-specific language, right? For you to specify, among these different elements that I want to display on my web page, maybe some of them has higher they should be more visible than others, right? And then with those information, maybe we can automatically consider, then maybe you want to do your layout, right? Or do your display in a particular way so that you can optimize your performance while the user still get the value, right, from the data that is generated. So that was something that we thought about. I still think potentially, right? I think there's just too much burden for people to understand each layer, or even for compiler to understand each layer. So I do think, and I hope in the future that there could be a holistic way for users to just specify their need. And there'll be some engine that's just going to automatically spit out, right, application code and database code. So that's the hope, but how realistic it is, we will need to see.
Okay, thanks.
Okay, thank you all. Yeah, so a lot of tools, so I don't have time to go through the detail. A lot of tools actually we have, you can find our source code or you can download them in the IDE. So welcome to, visit our project webpage. Thank you.
Yeah, thanks again, Shan. So, close.